Welcome back to part 2. We'll carry on from exactly where we left off in part 1 and start looking at some of the more complex features we will need to understand in any practical PCB.
Okay, so let's look at a couple of things that you'll see on more complex boards. One of the things you might want to do is right click on the PCB itself and lock it. It is very easy to move the PCB by mistake. Let's assume for a brief moment that that connector is there. I've got two orange wires crossing. I can't have that. They would obviously clash. How can I resolve it? Well, one simple resolution will be to move this wire to the top layer. But let's assume that's not possible, and we'll look at that in a moment. This bend point can be converted to a via. A via is a connector through the PCB that allows current to flow from the top layer to the bottom layer. And now we can move this piece of wire to the top layer. So that's in the top layer, that's in the bottom layer. It all works very nicely. Very important, very useful vias. They can be moved and they can be very fiddly, particularly when you're working on a larger board at lower magnification. But you need to grab them up in that corner and there they go. Okay, and you can put it anywhere you like. So that's a via. Very, very important to us. Other things you might want to do, you might want to put some text on the board. So there's a text option in the PCB view, comes up, defaults the logo. We can change that to say demo board, and then we can change its size. You grab the corner, and there we are, it says demo board. Bear in mind, of course, that this is an inch across this board, therefore that is very small. We're closing in at the end of this presentation, just really the last and perhaps one of the really important things to do. So we've designed our board. How do we get it into production? Well, the first step of that is to check that it is actually producible. At the top, in the routing menu, you will see something called Design Rules Check. So we do that. And it will go along and it will say, my sketch is ready for production. There are no connections or traces that overlap or are too close together. Excellent. On the other hand, if this via, for instance, were just overlapping that trace and we tried this, it would come back and say, oh, there's an error. There, there, and there. Now it's giving me 3 errors, but in fact it's all the one error. So we lose that and we say, oh dear, we need to move that. And we can check again. That is how you check that your board is ready for production. You can change those parameters. I never have. Leave them as default. It's very straightforward. There's two other things I want to touch on. The first are SMD components. I'll show you a bit more in the next part of the demo. But if we take the resistor there, and that's currently a THT, which is a standard resistor package. If we change it to an SMD, there we go, we now have an SMD resistor. Now because the SMD resistor is on the top layer, which is the default, these wires that were connected to it on the bottom layer are no longer connected to it, so we need to delete those. If we look at the schematic, it hasn't changed at all. If we look at the breadboard, it hasn't changed at all. There's clearly no scope for putting an SMD resistor on the breadboard. So now we have to put these wires back in place. The first thing you'll notice that despite the fact this was defaulting to the bottom layer, this will always be on the top layer. It has to be on the top layer because it's a SMD resistor. I'll come to that in a second, but there we go. We can straighten the wires out, lovely, and then we can take that one. There we are, and now we've got an SMD resistor. It really is as straightforward as that to use to design with SMD parts. Okay, but putting SMD or surface mount devices on the underside of the board is a tad more complex. The first thing we have to do is be looking at the underside of the board. We then go to the schematic and we take a resistor, drop that on there, go back to the PCB, do a Control-0 because I must be up there. See, it's my resistor over there. You will notice that is actually in orange. If I now change that to a SMD, it's an orange SMD. It's on the bottom layer. It is fiddly to get them on the bottom layer. You can't place them on the bottom layer. You can't move them to the bottom layer. You have to be looking at the bottom layer in the PCB view and then place them on the schematic. I can't move that resistor to the bottom layer. I have to be looking at the bottom layer when it's placed. That's a fiddle, but it does work, and it is a way of doing it. I think the very last thing then I'm going to touch on is putting on a ground plane. So it is quite good practice on virtually every board that you're going to make to put a ground plane. So I would suggest this is the very last thing you do. You finish your design, you make sure it works, you save a copy of it, and then you get another copy and another copy. In the routing menu, you do ground fill, top and bottom. There you are. And essentially what it's done is it's filled both the top layer and the bottom layer with copper to join all the grounds together. So it's well grounded, very free from interference, a good thing to do on the whole. Okay, so I think that concludes this particular stage of the demo. I'd just like to run through a couple of other examples just to show you some of the other things that can occur.
Now let's move on to a more realistic example. For this I have taken a pocket money project design from MERG, the Model Electronics Railway Group. I'm sure many of you will have heard of them, a very useful group with a wide range of electronics kits if you are interested in electronics and model railways. This design flashes an LED to emulate a variety of UK lighthouses by the insertion or removal of links, with code in a PIC microcontroller. But we don't have to understand the exact operation of the circuit for our purposes today.
Okay, so here's the MERG lighthouse circuit laid out on a breadboard in a very similar way to we've just seen in the previous example. I really want to talk about the IC. This is generic IC as contained in the parts list. Now, you can change a lot of things. You can change pin spacing, but 300mm is the standard pin spacing for a dual inline chip. You can change the number of pins, but it gives you some strange results for a part that's already partly connected. But it can be done, and that's fine. You can also edit the pin labels. This is very important. So here we could decide that pin 1 is plus 5 volts, and that's 0 volts, which it typically is on a PIC. And the other thing we can do is change its chip label. We want this to be a PIC, but we know exactly what PIC it is, so we might as well give it the correct number. And there you are. So now we know exactly what we're using in the final design. If at this stage we look at a schematic, it looks a bit like that. And as you can see, they are very spread apart, the parts, and the PCB in a very similar sort of way. If we now move to the next stage, we've sorted out the schematic. And there's a version of the schematic. As I've said before, you can draw the schematic in lots of different ways, but there's a version of the schematic. And you'll see now, because we put those details in, the IC has the proper name, and also we've labelled those pins. We could go around and label all the other pins as well if they have specific functions that we want to record. PCB still looks like that. The next stage, of course, is to resolve the PCB. So we've resolved the schematic, and now we've resolved the PCB as well. You can see this is a bit more cramped than the little demo we did just now, but nevertheless a fairly straightforward circuit. This PCB is 37mm by 22, set against the strip board version, which is 65 by 25, so about half the size. But we can go further. In this version, we've also converted the IC to be a surface mount component. In this case, you can see somebody's provided a graphical representation of the IC suitable for the breadboard. It doesn't make any difference at all to the schematic, but I have just laid this schematic out in a different sort of way, as I discussed earlier. It just shows you all the schematics that you've seen for this design work equally and are the same. Some people will find this an easier way of drawing their schematics for the circuit. The PCB then looks like that. In the middle there, you can see with these elongated terminals is the surface mount IC, complete with surface mount resistors, surface mount capacitor, whatever makes sense. Haven't done a surface mount regulator. Unless you need the height, it's probably not worth it. This comes out at 17 millimeters by 22 millimeters, which is half again of the one we've just looked at. So it just goes to show you can save a lot of space by designing your own PCB. I want now just to look at one last example. Here's a board I've designed for our layout. It has an H-bridge. We can drive a stepper motor as well as a variety of outputs that can drive servos, light LEDs, receive inputs and so on, all controlled by an Arduino Nano. And it has a CAN bus or C bus interface to interwork with the MERG layout control bus. One of the things I didn't touch on was this little box down here. It does give a more professional and neater solution. It doesn't really change anything, but it is helpful in letting you keep track of where you are. This box is a component which you find down here on a schematic view. That box there produces that box, and you take the corner and grab it up, and you then can frame your design within that. There are then a lot of different things you can fill in to hold the information that you require. The PCB looks like that, and now you can see it is getting a lot more crowded. You will note that I've used on my power lines, where possible, a wider track than standard, particularly as we're driving external components that may take more significant power than the standard ICs. You can do this for any track. If you select a particular track there, you can see the width over here, standard 24mm. You can choose finer tracks or wider tracks as you wish. I tend only to use standard and extra thick, but other ones are available if you're really short space, but be careful what you're doing. And that really is an example of where we are at the moment. I have to say this looks a very much neater board than the very first one I did, but that's progress and that's experience, and I'm sure you'll make equal progress or probably much better progress than I have.
The export from Fritzing will produce 10 files. These need to be combined in a zip file or similar. You now need to find someone to make it. The cheapest route, and the one I've always used, is the Chinese manufacturers. I've listed the 4 I've used, but there are others. I paid between £8 and £14 for 10 boards, depending on the exchange rate and the postage rates. The PCBs are usually less than $5, the rest is postage. I've not used the Fritzing built-in surface, so can't comment on the quality. But it is more expensive than the cheapest Chinese solutions, but might be better if you want a small number of boards quickly. Let's look at a typical Chinese PCB manufacturer's webpage.
Here, as an example, is the Seed webpage. They are all very similar. Click on the Add Gerber Files button and the browser will open, which will allow you to select your zip file. You will not save money with a smaller board. The standard options usually give the cheapest solutions. As you can see here, this is 10 100 by 100mm boards for $4.90. We'll look at the postage in a moment. On the Seed website, the color choices do not add money except for matte black. PCB thickness, different surface finish, etc., different weights of copper, all add significantly to the cost. If that PCB dimension was 110 by 100, so only marginally bigger, that cost would escalate from $4.90 to $33. So you do need to be very careful with those options. Now let's have a quick look at the postage. Here is a typical example of postage costs. These options seem to change with irregularity. I'm not clear on how the US Postal Service provides the cheapest service between China and the UK, but that's what it says. I've used Singapore Post on a number of occasions and it seems to have worked well. Typically the board is a week in prep and a week in manufacture, so you can expect it to take up to 6 weeks.
Creating new components is complicated. I've done it, but to me it's not easy. However, as most common component packages are available, it's not the drawback it might seem. I found it very straightforward, and if the limitations of fritzing are an issue, you are probably doing something far more complex and should probably be using one of the commercial software packages like Eagle or KiCad. I hope you found this short video helpful. I'm happy to answer any questions I can, but as I said at the start, I'm not an expert. Many thanks for watching. Goodbye.